We're back at it. Back to have you guys back. I'm glad to have you guys back for the last 2 weeks here, or at least 1 week for you guys. We pretty much have learned all the stuff that we need as far as new content goes. So what we're going to do is we're going to do some review this week. We have one new thing to learn, kind of, today. And then we're going to review the content. And we have a test on Friday. So let's talk really quickly about that. As far as the schedule goes. All right. So as you guys have probably heard me yell on and on about for the last on all the videos and stuff like that, we are now on December 7th. So today we're going to talk about orbitals and light. There's a little activity we're going to do. So I'm going to let those of you at home go a little bit early, and you guys will do this activity when you're in class next week. Tomorrow we're going to talk a little bit about making sure, because I don't know, I haven't seen you guys in 2 weeks, making sure you know all the history of the atom. We'll give you a full day on the 9th to do the actual review sheet. The 10th, you guys have the second half of the flame test lab, and then you'll have your test on the 11th. And that is going to be everything from starting back on the 16th of last month up until now, everything in the packet that you're holding. So that's kind of where we're headed for this week. And then for next week, just so you guys know where we're headed, we did decide to push back the exam. I use exam loosely. Okay. We just can't really start a whole new unit in 1 week before the break. And it is very good to always go back and think about everything in the semester. The semester exam is designed to force you to think one more time about some of the concepts we went over. So I'm going to give you guys the review packet on the Friday. So you guys physically will have a physical review packet this coming Friday. And then I will give everybody in class Monday, Tuesday, and Wednesday of next week to work on that review packet. Then you will have a semester exam. Okay. It will be in 45 minutes. Okay. So it's not this like double period stuff. So it will be in 45 minutes and it will be on Schoology. So it can't get that challenging if those ramifications are on it. And things like that. And then with the cohort that is here, they will do the second half of the flame test on that Friday, and you guys will then clearly not have anything. That'll be your day off, the remote week. Okay. So really, truly just reviewing and coasting on in here. Make sure we get a couple big tests. Oh, this test, they are changing the way the grades are done. So there's no semester exam grade. This will go into your second quarter grade, which I think could be a good thing because the test really should not be hard, okay, as long as you prepare for it. Okay, so that's kind of where we're going here. Wanted to make sure everybody was feeling swell with the schedule. Perfect. So guys, I will still have you guys call in Monday, Tuesday, Wednesday for right now. If we have everybody call in Monday and everybody feels great, we might adjust that. But let's just say, especially for participation points for next week, we'll start in definitely Monday, making sure you're calling in live so I can tell you what is on the exam, how many questions, all that kind of good stuff. We should have that by Monday. Okay, perfect. All right, so what I want to have you guys start to do is find in your packet atomic structure bellwork number 5. Atomic structure bellwork number 5. I would like for you to see, I'm going to walk around. I'll check with you guys at home. Oh, yay, so many more people. Okay. What is the difference between an orbit and an orbital? You might want to know who said each. In your own words, describe the shape of an SPD. And, I mean, you can draw them if you want. Number 2, I wouldn't ask you a question like that on the test or anything, but just seeing if you remember. I just don't even know if you even watched the lecture from last week, so hopefully. Alfvei's principle and Hund's rule, because we're going to need to be able to do those. Then there are some bubble sheets. See if you can't do a few electron configurations for me. I'm just walking around to see if you have any idea what you're doing, if you watched anything from the last 2 weeks, just trying to see where we're at. Those of you at home, I want to check in with you in just a second as well. So go through this and make sure that you can answer these. And you got the bubble sheets going on there as well. Make sure you can, and these are electron orbitals, right? Awesome. Good stuff. All right, coming around. And this quantum mechanics stuff is confusing. So let's make sure that you all Ask me if you have any questions. This stuff is tough. All right. So let's go ahead and see where we are at. Hopefully you're feeling good. So you guys wrote down the answers here. Let's check. And then if you have any questions, please don't hesitate to ask, okay? So the first thing, in orbit, I would know that Bohr is the scientist that is credited with this idea of an orbit. And an orbit is this definite, so we have a positive nucleus. An orbit is a definite path these electrons go on. He thought it was like planets around the sun. So it is a predictable path around the nucleus. And we're talking about electron movement, that the electrons kind of go around and around. And so if it's over here, then a minute later it'll be over there, and then it'll be over here, they'll be over there. So it was the predictability that we actually found was not correct. So to try to pay some homage to him and to make it extra confusing, they then came up with the idea of orbitals. So they're not these paths that electrons go on, but they're regions of space where there's a high probability of finding an electron. An electron is more likely than not to be in these spaces, okay? And then there were a couple different shapes. There was the S shape that was like a sphere, and those little models that I had for you. There are 3 P shapes that look like pears. There were 5 D shapes that I said kind of look like daisies, whatever. I mean, I just want you to know kind of the gist of the shapes. So when you go into college and they start talking about these shapes, you can have something in your mind when you go to that, okay? And then the last 2 scientists we learned about were Aufbau and Hund. And Aufbau says that electrons will fill the lowest energy level first. And what does that mean? That means closest to the nucleus. So when you're filling in your bubble sheet, you always start closest to the nucleus because that's the lowest amount of energy for an electron to reside, okay? And then Hund, because electrons are negative, both of them, negatives don't like to hang out near each other, so they will spread out as far as they can. So you put only 1 electron in an orbital at a time. Then you will, though, go back and double up, but you may not put any more than 2 in any one orbital. Okay, perfect. All right, so then we went ahead and we showed you the new chart, which is your new model of the atom. This is our current working model of the atom. There is a positive, small, dense nucleus with all the mass in it at the bottom. 1s is closest to the nucleus because this is a low amount of energy. And then when you go to fill this in, you look up nitrogen. He has an atomic number of 7, so therefore he'll have 7 electrons. So you start at the bottom because of Hund, or Aufbau, excuse me. 1, 2, 3, 4. So Aufbau says start here. And Hund says you need to go 1, 2, 3, 4, 5, 6, 7. Okay? Then that's lovely and everything to see these bubbles, but what they taught us next was a shorthand notation to write down what you saw. You simply write the energy level and the shape. So 1, S has how many slashes? 2. 2S has 2. And you get to 2P, and that has 3 electrons in it. Okay? You can get a little bit bigger here. Germanium, if you look him up, he has 32. So much fun. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Notice how I did 4S before I did 3D just because it's closer to the nucleus. Okay. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So when you write him out, you're going to end, you go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, ends with just 2 in it. Okay? And if you want the last 2, Chromium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. And silicon is 1s2, 2s2, 2p6, 3s2, 3p2. Okay. So again, what is this telling us? You're like, I don't know, I just write numbers and letters. Okay, this is telling you where the electrons are. Or probably are around the nucleus. Okay, perfect. Now, what I want to do is you do have another practice sheet if you would like. So the next page in your packet is orbitals practice number 2. If you would like, more than welcome to do that. Okay, and the key is in the Monday folder. However, what I want to have you do is actually go backwards in time in your packet. And I want you to find the rest of the notes. You're probably like, well, she didn't go over that. That's silly. And if you go back to notes number 5, it should only probably be 2 pages back. We'll pass the flame test. 3 pages back. History of the atoms, notes number 5 on the back. I just like abruptly stopped. It's a little bit per design here. All right, so I did not have you around very much when we were talking about how atoms emit light, so hopefully everybody understands, so don't write any of this down. We were using the Bohr's model when we first described how atoms emit light, okay? The first thing that happens before an atom emits light and everything normal is that the atom is what's called at ground state. That means the electrons are close to the nucleus and they have a low amount of energy. So your electrons are chilling down here, and this is Bohr's model. We're about to take it into orbitals, and that's fine. Okay. Then you have to add energy. And so what we did was we put it either in a fire, or that's how the lights work above our head. You turn on the electrical energy. Today you're going to use kinetic energy. So as long as you add energy, these electrons can then jump out, okay, to higher energy levels, and that's called bleep, the excited state. And that's when your electrons are further away from the nucleus because they have higher energy. Now, if you add energy to go out, you also can't stay there forever. What goes up must come down. So when the electrons fall back down, and this is what you saw with the burnt. You saw the little barcode demo we showed you. When they fall back down to the ground state, as they do, they release a photon of light, okay? And a photon, depending on how far they fall, will give you a different color. Remember, high energy on the violet side and low energy, so it had a small fall. Okay, so again, it depends. If you fall from a long way, you're going to be closer to the blues and the purples. If you fall from a short way, you're going to be closer to the reds and the oranges. So that's what we had already talked about in the notes. The last thing that I want to do here is I would like to turn this into how this works with orbitals. So you're writing this down. You're on the back here. So electrons start at the lowest energy level possible, except for when is Aufbau violated? Aufbau is violated when you have the excited state. Okay. When your electrons gain energy and jump up, they are momentarily breaking Aufbau, but they will always come back to him. I'll always come back down. Okay. Awesome. So let's go through and let's write how light is emitted using our newer understanding, which is orbital. Now, this is like kind of small, so you can write smaller on yours, and I can on my smartboard. So this is the exact same thing. We're going to do sodium. If you look up sodium, he has an atomic number of what? 11, correct? So we're going to do 11 electrons. So this is the same thing. I just blew mine up a little bit bigger. So what we're going to start with is the ground state. I would write this down on your little packet here. The ground state has low energy, and I wrote ease are close to the nucleus. So if I asked you on your test on Friday, what a picture of a sodium is the one we're doing, a sodium atom in its ground state looks like using orbitals, you would draw it normally, how it's supposed to be, correct? So let's go ahead and do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's ground state, my friends. How you normally do it. Awesome. Now, how does an atom emit light using an orbital chart? After step 1, step 2, you have to add energy. You have to add energy. And when I add energy, remember down here is the nucleus. When I add energy, those electrons are going to jump. So all you have to do, if I asked you what would be the orbital chart for the excited state, now there is a mathematical equation you can do to figure out exactly how high they're going to jump. That's not for us. You just take your 11 electrons and you just put them up. So we got, I don't know, they're usually down here, maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Do not violate Hund's rule while you do this, though. You're only breaking Aufbau. So this would be a snapshot of the excited state where your electrons have high energy and they're far away from the nucleus. Okay, awesome. Now they can't stay up there forever. So what will happen to this electron? It will fall back down. And as he falls back down, then you get yourself a photon. Okay, so that's the last thing you have to understand as far as taking our understanding of how atoms emit light and transforming that into an understanding in the actual orbital chart, which isn't that if you understand that they jump away from the nucleus and fall back down. If you understand what an orbital chart is, this probably isn't a stretch. Okay, awesome. So what we're going to do the rest of the time is I have a demonstration, a little activity for, oh, wait, I want to do one with you, those people at home. Good stuff, good stuff. If you want to fire up your Chromebooks at this point, you can, because you will be doing your lecture questions. All right, so just to kind of show you another fun way that you can see this process. I'm going to drop this camera here. I have some lasers here and some very special paper that's called phosphorescent paper. And what phosphorescent paper will do is it will emit light when you've given it enough energy from light, which I know sounds really weird, but. All right. So we got some phosphorescent paper right here. It's this green paper you're looking at. And I have 3 lasers. I have a red laser. As far as light goes, does red have a lot of energy in it? Yes or no? No, it doesn't. Okay. So not much happens on this paper when I put a red laser on there. Some people say they can see stuff. Can you see stuff? A little bit. Okay. Next level, or that's purple. We don't want to do that next. A little bit higher energy is green. Okay. So you can maybe start to see, those of you in person maybe, can start to see some light being emitted from our lovely little phosphorescent paper. Okay. Because that had a little more energy. But then we know the big kahuna of energy is purple. So these photons that are being released from my laser have a ton of energy, so much energy okay, that they can actually give that energy to that paper, and that paper, the electrons in the paper here are taking the energy, they're jumping and falling and jumping and falling and jumping and falling, and as they fall, they release their own green color. Okay, so you can be like, smiley face. You know how hard it is to draw. Almost. There we go. Okay, I'm trying again. I need to like get better from drawing from a distance. There it is. Oh my God, everybody's home for a Monday. All right. So again, this is called phosphorescent paper. And the only thing that works on this is really well is the purple photon, because the purple photon has so much more energy in it. Okay, so if you're thinking about your colors, red is lowest and purple is the highest. All right. Good stuff, good stuff. And then the last thing we're going to do in class in the last, we got 10 minutes. Should be enough time. We're going to do what's called triboluminescence. So you can get atoms to emit energy or atoms to emit light by burning them, running electricity through them, by giving them energy with lasers, with other light, or you can also give them energy by like manually, physically giving them kinetic energy. So we're going to do that at home. However, you people here, our Orbitals in school, you people at home can't see this. So if you are at home and you have any questions, hang around. But if you don't have any questions, you guys are going to do triboluminescence when you come back next week. Okay. So those of you at home, if you don't have any questions, do your review, your lecture questions. Were they open? Could you get into them? Perfect. Do your lecture questions, and then you guys are done a little bit early because we're going to do an activity in class, and you guys will do this next week. Thanks for coming, guys. All right.